Survey of Calculus, Chapter 1, Section 5, Differentiation Techniques, the Power, and some Difference Rules. Now, remember that the derivative is simply the slope of the line that is tangent to the curve at a given point. Also remember that the formula for the slope of a line is the change in y over the change in x. Now, we can symbolize the slope formula using the notation delta y over delta x. The triangle is the Greek letter delta, and it represents change in math and I believe in science as well. This notation leads us to a notation for derivatives that was invented by the German mathematician Leibniz. His notation is, instead of delta y over delta x, it's dy over dx. The idea being the same. It's the change in y over the change in x. And it is read the derivative of y with respect to x. So right now we have these four ways of indicating that we want to do a derivative. We have Leibniz notation, the dy over dx. It can also be written as d over dx f of x, where the function is put there instead of a y. It can be written as f prime of x, and we've seen that already, and you could also write it simply as y prime. When we want to take a derivative at a specific value for x, there's a couple of ways we can show that. One is the dy dx, and we have a line, and at the bottom of the line, x equals 2. This tells us to take the derivative of the function, and once we have the derivative, put in 2 for x and solve. The second way to indicate that we want to do this is f prime of 2. Again, take the derivative, get the equation for the derivative, and then put 2 in place of x. These derivatives we calculated in the last section in different examples. You see on the right there where it tells what example we did these in the last section. You can look in the book and find them. We saw that x squared was 2x, or 2x to the first. We found that x to the third was 3x squared, and x to the fourth was 4x to the third. And then x to the negative 1 is negative 1 over x squared, and so forth. Now, I told you in the last video that you should try to look for patterns as you solve these. And hopefully you are seeing a pattern here with these powers. So notice that what we do when we take a derivative of a variable to a power, what happens is the power comes down in front and becomes a coefficient, and then the power in the variable drops by 1. So x squared, the 2 comes down front, and the power is reduced to 1, and we have 2x to the first. X cubed, the 3 comes down front, and then the power reduces to 2, 3x to the second. This applies not just to positive integers, but also to negative integers and fractional powers as well. So our first theorem is the power rule. It says for any real number k, if y equals x to the k, then the derivative of x to the k is k times x to the k minus 1. And this is just a generalization of that pattern that we saw. All right, now try this example. Find the derivatives for these three functions. Pause the recording to do it and resume to check your answer. All right, here we go. These are worked out using the power rule. Now, you don't necessarily need to show every single step here, and the more you use them, the quicker you'll be able to do them. So check your answer, see how you did, look at the process if you made a mistake. Okay, now try these. Let me remind you that a root can be written as a power, as a fractional power. So the fifth root of x is the same as x to the 1/5 power. Pause the recording, give these a try, and resume to check your answer. Okay, same process. What we're going to do is bring the power down front and then reduce the power by 1. Now, we don't want to leave a negative power, so we do want to write that as 1 over. And notice also that the power was rewritten as a root. Now, interestingly enough, in calculus, you can kind of get away without rationalizing the denominator. So, all these years you had to rationalize it. In calculus, we can actually get away without doing that. It's a little bonus, you don't have to do that extra step. And then B, the same idea. These two problems, pause the recording, give them a try, and resume to check your answer. All right, for the first one, we get 15x to the 14th. For the second one, negative 7x to the minus 8th, or you could write negative 7 over x to the 8th. Be careful with these negative powers. It's really easy to accidentally, when you're subtracting, think, okay, well, negative 7 minus 1 is negative 6. It's not. It is negative 8, and the negatives are the powers that people are going to make the most mistakes on doing this. Now consider the constant function that you see here. The constant function is f of x equals c. It's a horizontal line that goes through c on the y-axis. And we've got 2 points designated here. We've got x and then x plus h. And notice that the slope of any horizontal line, or recall that the slope of any horizontal line, is 0. So we know the slope of this line is 0. That leads us to Theorem 2. The derivative of a constant function is 0, which makes sense. The slope of the line is 0. Theorem 3 says the derivative of a constant times a function is the constant times the derivative of the function. So in other words, if you have the derivative of, say, 3x squared, you can make that 3 times the derivative of x squared. So knowing that, try these out. Pause the recording, give them a try, and resume to check your answer. Okay, notice what we're doing. The 7x to the fourth, we pull the 7 out front. We do the derivative of x to the fourth, and we then combine and get 28x to the third. And the note says, with practice, you can do this in one step. So you will get to the place, if you're not there already, where you don't need to split it up like this. But it's important that you understand why you can do what you're doing. Okay, as you look through the rest of these, if you're wondering about part B, we have negative 9 times the derivative of x. X is x to the first power. Bring the 1 down front and reduce by 1, and that gives us 1 times x to the 0 power. Well, anything to the 0 power is just 1, so that's why the derivative of x is just 1. Here's another one. Give these 3 a try, and then pause the recording to do that, and resume to check your answer. Okay, see how you did. It's really important to remember that pi is a constant, so don't treat it like a variable. All right, now we're going to have an application problem. The volume of a spherical tumor can be approximated by this equation. Find the rate of change of the volume with respect to the radius. In other words, take the derivative. Okay, instead of dy dx, this would be dv dr. And then find the rate of change of the volume at 1.2. In other words, once you found A, put in 1.2 for R and give a number answer. Pause the recording, give this a try, and resume to check your answer. Okay, so taking the derivative, the 4/3 is a constant. The 3 comes out front. 3 times 4/3 is just 4. Pi is a constant, so it stays pi, and then the power on the r reduces by 1, so 4 pi r squared. And that actually, incidentally, happens to be the formula for the surface area of a sphere. And then what we do for the second part is we just put in 1.2 for r, and we get 18 centimeters squared. What that means is that when the radius of the tumor is 1.2 centimeters, the volume is changing at the rate of 18 cubic centimeters for every change of 1 centimeter in the radius. So it tells you how fast things are changing. Okay, Theorem 4. This is actually a pretty easy and common sense rule. This just says that when you have, you're taking the derivative of things added together, you can just take the derivative of each part and then add the results. The same for subtraction. Find these derivatives. Pause the recording, give it a try, and resume to check your answer. Okay, here we go. And notice what we're doing is we're just taking the derivative of 5x to the third, the derivative of 7, and subtracting the results. The same for b. The derivative of 24x, the derivative of the square root of x, the derivative of 5 over x, and then put a minus between everything. Now try this problem. Pause the recording, give it a try, and resume to check your answer. It's really desirable when you have powers, when you have roots, and when you have x's in the denominator, that you, first of all, make any x's that are in the denominator, change those to x to a negative power. And if you have a root, change the root to a power expression, as you see here. Okay, that one was a little more complicated. If you made your way all the way through that without any mistakes, congratulations. Okay, a little word of caution. The derivative of f of x plus c, which is a function plus a constant, is just the derivative of f of x. The derivative of c times f of x is a function times a constant, and it's the constant times the derivative. So just kind of make sure you know the difference between those two things. If the constant's being multiplied, it's actually going to stay there. But if it's not being multiplied, if it's being added or subtracted, it will go away. Okay, now try this problem. Pause your recording, give this a try, and resume to check your answer. And do a little thinking on this one. Find any points on the graph for which the tangent line is horizontal. You have to think to yourself, what kind of slope does a horizontal line have? And it has a slope of 0. So in other words, you want to find out where is the derivative equal to 0. So take the derivative, set it equal to 0, and solve. And we get two places, when x is 0, when x is 4. But we're actually not quite done because you do need to find the actual points. So put those back into the equation and get the y values that match. See here? And then you can see on the graph where those two spots are. Interesting to note, those are going to be at the maximum and the minimum, at a local maximum and minimum there. For part B, we want to see where the derivative equals 9. So we're doing the same thing, except instead of setting it equal to 0, we set it equal to 9. And then we're going to factor that. We're going to solve. We get our values for x. We find the matching values for y, and you can see those 2 points there on the graph. Here's a summary of what we've done in this section. So if you want to pause and read over this, and then resume to continue. Okay, the rest of this video is additional practice, so pause the recording, give these problems a try, resume to check your answer, and proceed that way through the rest of the recording.